Greetings and welcome to the video for problem set number 6 of Chemistry 223, where we're going to look at both Chapter 19 and Chapter 21. First of all, congratulations. You are at the very last problem set of Chemistry 223, and that's pretty freaking awesome. So pat yourself on the back for me and know I'm very proud of your hard work and stuff. It's really appreciated. This problem set, like the other problem sets, will be really similar. You should use the periodic table found at mhchem.org/per-tab. You should make sure that you self-correct all your problems. The problems you get right, put some kind of self-correct symbol next to it. The problems you get wrong, just cross out the old answer, at least write in the new answer, maybe make some notes as to how you do better the next time. You turn in a problem set with lots of self-corrections and you will do great. If you have questions on this material, check out the Avid/LSC Center located above the library on the main MHCC campus. Their website is mhcc.edu/avid. Free chemistry tutoring is a pretty cool thing. They're pretty awesome. And of course, you can also talk to me. I'm happy to help you on this material. So it's kind of cool chapter, great way to end the term, and let's get into it. You will need a couple of handouts, though, for this problem set. We're going to be looking at the nomenclature, the naming of two different systems. And the organic chemistry naming is going to be probably the weirdest one, but it's nothing you can't do. First of all, I think you'll need a copy of the Geometry and Polarity Guide. We used this back in Chemistry 221. It has all the electron pair geometry, molecular geometry, polarity, stuff like that. Might be helpful as you're writing out these different structures. So mhchem.org/GeoPo is the way to get that. You'll also, I think, benefit from having the Organic Chemistry Guide next to you. That's at mhchem.org/OCG. And the Organic Chemistry Lab also has a lot of information in it, which is pretty helpful. That can be found at mhchem.org/OCL. So if you have these things next to you, you should be good to go. And of course, if you have questions, let me know about them too. I can help out. Okay, let's get into this final problem set of Chemistry 223. Identify two transition metal ions with the following electron configurations. And you can see argon 3d6, argon 3d10, etc., etc. The important thing about this is that when you're making an ion with a transition metal, the 4s electrons come out first, all right, if you have any, and most of them do. And after that, you can do it. Now, there's going to also be several answers for many of these questions, so I'm just letting you know that off the top of the head. So for the first one, notice that if you took out 4s2 from the first one, you'd have argon 3d6. If you would count over 6 elements on the periodic table, that's iron. So iron plus 2 is a good example of this. Now, iron, neutral iron, is argon 4s2 3d6. And if you're going to take away 2 electrons, which is what positive 2 is, the 4s comes out first. Higher n comes out before 3d. So iron plus 2 is going to have an argon 3d6 configuration. You can do the same kind of thing with cobalt. Cobalt is an argon 4s2 3d7. So to make cobalt plus 3, you would take away the 2 electrons in 4s first and 1 electron from the 3d7, making it 3d6. You'd be good to go. And of course, you don't have to stop there. You could have a nickel 4+, which is rare, but it's a possible answer here and stuff. Any of those would be fine answers. Now, for the next one, it's not quite as obvious. Zinc is argon 4s2 3d10, so zinc plus 2 is a great one. You could take away 2 electrons, make it argon 3d10. Copper plus is a thing that's an exception to the n+L rule. Normally, you would think copper would have a argon 4s2 3d9 configuration, but because of one of the weird exceptions, which happens for chromium and copper and several other ones later on, copper actually has an argon 4s1 3d10 configuration when it's neutral. So copper plus 1 then would have an argon 3d10 as well, which is kind of strange. Now, argon 3d5, all right, could come from an argon 4s2 3d5, which is manganese. Take away 2 electrons from there and you'd have the 3d5. But you could also do that for iron plus 3. If you took away 3 electrons from the argon 4s2 3d6, you'd initially have argon 4s2 gone, so argon 3d6 for Fe plus 2 like we saw in A, but this is iron plus 3, so it would have a 3d5 as well. The next one, argon 3d8, if you took away 2 electrons from nickel, all right, that would be an argon. It would no longer be argon 4s2 3d8, but it would be argon 3d8, all right. And then copper 3 plus, we saw earlier, was a 4s1 3d10. So for taking away 3 electrons, the first one would be the 4s, and the next 2 would be 3ds. So you'd end up with an argon 3d8 as well. So good experience making ions from the transition metals. Transition metals almost always make positive ions, so that's why this is important to what we're doing. Give the oxidation number of the metal in each of the following complexes. Now, all of these are complex ions. They all have a charge next to it. That's where the complex comes from. And if we know the charges on not only the metal and the ligands as well, the pieces in the outside, then that all of those charges together will equal the charge on the complex. So for example, in the first one, the charge on the iron plus the charge on the ammonia times 6 equals positive 2. So we have to know the ligand to figure out the variable charge metal. Big surprise there. Ammonia is a neutral ion. It does not have a charge. So that means if ammonia is neutral, the positive 2 on the complex equals the positive 2 on the iron. So this iron is a positive 2 charge. Ammonia is neutral. Now on the next one, it might be tempting to say, oh, zinc is a negative 2 ion, but don't do that because zinc, like most metals, is almost never negative, all right? And actually we would predict based on the zinc and the stairs on the transition, on the periodic table, that zinc is a positive 2. So if you look up or if you remember, cyanide, CN, has a negative 1 charge, and there are 4 negative 1 cyanides plus zinc equals negative 2. So if you add 4 to both sides, you get the zinc by itself. You should see that zinc is indeed a positive 2 charge. Zinc is positive 2 because cyanide is negative 1. And again, it's like zinc plus 4 negative 1 cyanides equals negative 2, and the negative 2 came from there. So again, if you solve that silly equation, then zinc equals 4 minus 2, zinc equals positive 2. All right, cool. Now the next one has a cobalt. It has 5 ammonias and a nitrite, NO2 minus. We saw earlier that ammonia is a neutral charge, so it doesn't have any charge. You don't have to worry about that. But nitrite has a negative 1 charge. So you have cobalt plus the neutral ammonias, which don't really count, and a negative 1 on nitrite. All of that equals positive 1. And so if you do the math, cobalt here comes out to be positive 2. Ammonia is neutral. NO2 has a negative 1 charge. If you put the negative 1 on the other side, negative 1 becomes positive 1. If you add that to the positive 1 that's already there, cobalt plus 2. And the last one has En, that's ethylene diamine. Ethylene diamine is a big neutral ion. It takes up 2 places around the coordination sphere, which we'll talk about. We talked about in lecture, we will talk about. But the important thing for us, it has no charge. It's a neutral ligand. So that positive 2 means that copper here is a positive 2 ion as well. Right formulas for the following ions or compounds. All right. So this is one of the ones where the names look kind of crazy at first, but really it's not too bad. You just have to kind of break it down, and I'll help you do that in this first one. So let's look at this first one. The full name is just crazy. Diamine triaqua hydroxychromium 2 nitrate. Oh my goodness. Again, let's break it down. So Greek prefixes, di is 2 and tri is 3. And this amine with 2 M's means ammonia. ammonia. And the aqua means water. Hydroxo is hydroxide, OH minus. And we've got a chromium 2, so that's chromium plus 2. Now, first of all, let's see if we can do just the part on the left, and we'll worry about the nitrate here in a little bit. Now, amines, ammonia, are neutral, and water is neutral. But hydroxo is a -1 hydroxide. So if we combine that then with a chromium plus 2, we're going to have an overall +1 charge for the complex ion. And the reason we waited on nitrate's -1. So it looks like we're going to need a -1 nitrate to balance the complex ion over there. So this whole thing, when all is said and done, we put in square brackets the complex ion, CrNH32, H2O3, OH. And again, 2 ammonias, NH32, 3 aquas, 3 waters, H2O3. The hydroxo is the OH. And because chromium was +2 and hydroxide's -1, the complex ion, the part in the square brackets, has a +1 charge. Nitrate balances out with a -1. Woohoo! We figured out the formula. Oh, exciting. Next one. There's a Greek prefix, hexa, that means 6. 6 ammonias. So this is going to be iron, Fe, with NH3, 6. And notice that this is an iron +3. Now, ammonia doesn't have a charge. This is iron +3. Nitrate's -1. We need to make it neutral. So it looks like we're going to need 3 nitrates. So in square brackets, we will write Fe, NH3, 6. That's the hexaamine iron 3 ion. That has a +3 charge. We're going to make it neutral. So we're going to add 3 -1 nitrates to it. We are good to go. If it wasn't neutral, it would say hexaamine iron 3 ion, something like that. And that would imply you didn't have the 3 nitrates, and we'd have a 3+ in the upper right corner of the square brackets around the complex ion. But this has a nitrate, so we're good to go. Now, the next one, pentacarbonyl iron 0. Now, penta is 5, carbonyl is CO, carbon monoxide, and it's iron 0. Iron 0 literally means iron without a charge, neutral iron. So this one's actually pretty chill. You'd write FeCO5 like that. People usually put it in brackets. You don't really have to sometimes, but that's the best way. Pretty mellow, not too hard. And then the next one, ammonium tetrachlorocuprate 2. Now, this is an example where the metal is in the negative part of the ion. Remember, an ionic compound always has a cation and an anion, a positive and a negative part. And if you see that ATE ending, that means it's on the negative part. So cuprate, that's a copper +2, but it's in the negative. It's negative because it's tetrachloro, 4 Cl's. Copper +2 and 4 Cl minuses, that complex ion is going to have a -2. Ammonium is a +1. So you're going to need 2 ammoniums to balance that CuCl4, and you'll be good to go. So the formula here, ammonium taken twice, NH4 twice, and then square brackets CuCl4. We have some formulas. We need to find the name of the ions or the compounds. All right, no problem. The complex ion is designated by the square brackets. All right, and we'll need to figure out the charges on the metals, use the Greek prefixes, etc., etc. So for the first one, notice that there's an overall +1 charge, and there's also 2 -1 chlorides and 4 neutral waters. So the cobalt has to balance the +2 for the 2 -1 chlorides, and also give a +1 for the outside. That's going to be a cobalt +3. And for the aqua waters and the chloros, you want to put things in alphabetical order. Tetra aqua would be 4 waters, dichloro 2 chlorines, cobalt 3 for the charge on the cobalt, ion. It's an ion because it has a charge. Notice that the next one doesn't have a charge at the end, so that's not going to have the ion name. But this one, we do want to have the charge on it, so it is an ion. Tetra-aqua dichloro cobalt 3 ion. Woohoo! The next one, cobalt with 3 waters and 3 fluorides. And fluoride, like chloride on the last one, is -1. So this is going to be a cobalt plus 3. We're going to have aqua and fluoro for the ligands. Alphabetical is the way to go. Aqua before fluoro, and tri in both cases. This thing is called tri-aqua, tri-fluoro, cobalt 3. It's not positive negative, so we don't need to add an ion. This is a neutral compound. Tri-aqua, tri-fluoro, cobalt 3. Good to go. And again, remember, we found the cobalt from the 3 -1 fluorides. The next one, we have a platinum, but platinum is in a -1 complex ion. So this one isn't going to be a platinum ion, it's going to be a platinate. You're going to have an ATE ending. Now this thing has ammonia, which is amine in this world, and you also have a tribromo because of the 3 bromines. Now there's 3 -1 bromines, but there's an overall charge of just -1. So the platinum here has a +2 charge. So remembering that amine from the ammonia comes before the bromo of bromine, this is going to be amine tribromo platinate 2 ion. Ammonia first, alphabetically, before bromo, tribromo for 3. 3 -1 BRs and a +2 platinum gives the overall -1 charge, but we're going to call it platinate because it's part of the part of a negative complex ion. So the negative ions get the ATEs instead of the regular ones. Finally, this last one is going to be an ion. It has an overall +2 charge. It's got a cobalt. It has an ethylene diamine, that's the EN. It has 3 ammonias and a chlorine. Now chlorine is -1, so that means it's going to take one of the pieces away. But ethylene diamine, EN, and ammonia are both neutral. So if there's a -1 Cl but an overall +2, that cobalt has to be a +3, because +3 cobalt minus 1 for the Cl gives an overall +2 charge. Ethylene diamine is also one that deserves a comment. Ethylene diamine has a Greek prefix in the name. So if the ligand has a Greek prefix in the name, you use the alternative method, bis, tris, tetrakis, and stuff like that. In this one, though, because there's only one, it's not really necessary. So amine comes before ethylene diamine. So this thing is triamine, 3 ammonias. Chloro, it comes after amine because alphabetically chloro is after amine, but before eth. And then finally, 1 ethylene diamine. We don't need the weird system. Triamine, chloro, ethylene diamine, cobalt 3 ion would be the name of this. That's a pretty long name, but you can break it down and stuff, figure it out. No problem at all. We're going to revisit the idea of geometrical isomers when it comes to coordination, compounds, and complex ions. And it says if the isomers are possible, draw the structures, label them cis, trans, fac, and mir. We'll talk about that. The first one is kind of like the one we saw earlier with the aquas. And notice that in COH2O4 Cl2, there are 2 Cls. And those 2 Cls on an octahedral cobalt. And by the way, I know it's octahedral because there are 4 waters and 2 chlorines, so 6 pieces total. So in an octahedral cobalt, you could have those Cls at 90 degrees, or you could have them at 180 degrees. So the first one definitely represents cis and trans. And you can see there how the trans means the chlorines are 180 degrees from each other. On the other hand, the cis, the chlorines there are at 90 degrees from each other. So this is what it means to be cis and trans when it comes to inorganic compounds. Now the second one, you can see that there are 3 fluorines, all right, 3 ammonias as well, but let's focus on the fluorines. I think think they're easier to see. And again, cobalt is octahedral because there's a total of 6 pieces. This leads us to the idea of what's called Fac and Mer isomers. Fac means face, facial. It's the face of an octahedron, which doesn't really need to concern us, but that's where it comes from. Meridional is the other one. The punchline here is that when you have meridional, there is an 180-degree bond angle between two of the like atoms. And on the Fac or facial isomer, you can see that all of these bond angles are 90 degrees. Mer is kind of like trans in the previous. It means that it's less polar. It's less polar because in this case, that FCOF angle, those will cancel each other out. Likewise, the ammonia CO ammonia at 180 degrees will wipe each other out. But in the Fac, you don't have any of this 180 degrees kind of canceling of polarity. So Fac is usually more polar, just like cis is more polar. And Mer is usually less polar, just like trans is less polar. It only happens again if you have 3 atoms that are the same in an octahedral complex, so you're good to go. The next one with platinum in this case has 1 ammonia and 3 bromides, so 4 pieces total. And regardless if you think of this as a square planar or a tetrahedral arrangement, there's only going to be 1 possible isomer. So in this case, there's no geometric isomers possible. Like you can't have cis and trans, you can't have mer and fac, you don't have enough pieces. And play with this if you don't believe me, it's totally true. But when there's 4 pieces and only one of them's different, you won't have mer fac or cis trans. The next one has 2 ethylene diamines, an ammonia, and a chlorine. Now this one's going to be octahedral, and it may not look that way at first, but 1 NH3, 1 Cl, and 2 ethylene diamines. But each ethylene diamine is what they call bidentate. It connects twice. So if each ethylene diamine connects twice, then you have a total of 4 connections from the ethylene diamine. You have an ammonia and a chlorine. That's 6 connections total. This will be octahedral. And if you think about this long enough, this one actually has cis and trans as well, but it's a little weird. So here's pictures, because a picture is worth 1,000 words. Trans, like I said earlier, means 180 degrees. And notice on the diagram on the left, the ethylene diamines, which have nitrogens there, and they've got kind of a CH2CH2 line drawing to the left and right. The nitrogens are at 180 degrees on the left version, and on the right version, you can see that ethylene diamine kind of loops up and to the right. So it certainly is not trans, and they call it cis, although I find that a little strange, but anyway, that's my personal preference. This one definitely has a cis and trans thing due to the ethylene diamines, and this just shows how this can all work out. Now, the last one requires a little special definition. 2-butanol is if you have 4 carbons in a row, 1, 2, 3, 4, and butanol means that there's an OH group on the end. So my real crude structure right there, which looks pretty lame honestly, is right there. But why this is important is I want you to focus on carbon number 2, which I put an arrow to. And that carbon number 2 has an OH on the top, a hydrogen on the bottom, a CH3 or carbon on the left, and an ethyl group CH2CH3 on the right. Notice how there are 4 different groups around that carbon. And if you have 4 groups around a central atom that are all different, this leads to what's called an optical isomer. And if you look down here, this is an example of what I mean. Optical isomers are what create different orientations if you send plain polarized light through them. And this is another kind of isomer. But again, the punchline is you have to have 4 different groups around the central atom. This is similar to what you have with your hands. If you have your hands and you look at the left and the right, they're the same. They have 5 fingers, 1 thumb, 1 pinky, etc., but they're not the same. Like you can't put them on top of each other. In chemistry, you have the handedness or enantiomers if you have this kind of behavior. And one simple way to check is that if your central atom has 4 different groups around it, you will have optical isomers. This extends to inorganic complexes as well. You can have a metal in the center with 4 different groups, and you can have optical isomers isomerism as well. So just be on the lookout for this. This is a little weird, but you'll see it in organic chemistry as well as inorganic chemistry. Pretty wild stuff. What is the molecular formula of an alkane with 6 carbon atoms? And then it says to draw and name the 5 isomers. Okay, so an alkane is the simplest of the organic chemistry groups. An alkane is an alkyl group, one of the building blocks of chemistry, with just a hydrogen connected to it. And alkanes are sometimes called saturated hydrocarbons because every carbon position has just single bonds, and the carbons are either connected to other carbons or they're connected to hydrogens. Alkanes have the general formula CnH2n plus 2. So if you know the number of carbons, like we do in the first question, we can use that value, which is n in that equation, and figure out the number of hydrogens. So if we have 6 carbons, n is 6, and the number of hydrogens equals 2n plus 2, so 2 times 6 plus 2, the formula here should be C6H14. And C6H14 is what they call a hexane molecule. All right, when there are 6 carbons, you take the hexyl group and you turn it into hexane. Cool. Just because we have a formula, C6H14, it doesn't mean we have all of the isomers. C6H14, there's many different ways you can draw it, okay? And one way to draw it is to literally just have 6 carbons in a row, 3, 4, 5, 6. And if every one of those hydrogen or carbon positions is filled up with hydrogen, because remember, carbon has to have 4 bonds total. So I just drew 3 hydrogens around that outside carbon. That carbon has 3 bonds to hydrogen and 1 single bond to the other carbon. That would be a happy carbon. It has its octet. This organic chemistry is mostly about giving carbon its octet, by the way. Anyway, on the next carbon, it would need only 2 hydrogens, because that carbon has a bond on both the left and the right to carbon, so it only needs 2 more bonds. That's a real sloppy H. I'm sorry. There we go. So those inside carbons only need 2 hydrogens. And you can add on other hydrogens as necessary. Again, the goal giving everything 4 bonds and octet. And then at the very end, just like the very end one on the left side, that carbon is going to need 3 hydrogens around it. So this molecule I've just written is what I call a straight chain alkane. There's literally 6 carbons in a row, and every position around the carbons either has a single bond to another carbon or hydrogens. And so if you count up the number of hydrogens, there are 14 there. This is C6H14. They call this compound N-hexane. The N stands for normal, which is like normal chain, I guess. So if you have all of the carbons in a row, that's when you're going to have the regular N-hexane. It's not always, though, that quite easy, because as we talked about in lecture, sometimes the outside groups, you can swap them. So for example, we could swap this CH3 and that hydrogen right there. And if you do that, now I only have 1, 2, 3, 4, 5 carbons, and I have a CH3, which was on the end, in this position. And again, same kind of thing, hydrogens around all the other positions. This thing also has 6 carbons and 14 hydrogens. So this is also a hexane isomer, okay? But while the first one with 6 carbons in a row was an N-hexane, showing that all of them are in a long row, this one, we have to think about what the new name is, because the longest chain of carbons is no longer 6. And indeed, let me change pens, indeed, the longest chain of carbon atoms right now is actually 5. That's the longest chain of carbon atoms in a row. I can't go back to the other CH3 without going backwards, which you can't do, all right? You have to just keep going in a straight line and stop. So this compound is a pentane. That would be the base name of it because 5 carbons is pentane. And the methyl group, which isn't part of that longest chain, will go in front. So this compound is going to be some kind of methyl pentane. But you have to tell the scientists where the methyl group is. So scientists will use the smallest numbers to tell which carbon that methyl group is off. And like I said in lecture, I recommend that you count from both left to right, which is what I've done right there. And I recommend that you count right to left. So 1, 2, 3, 4, 5. Now, I'm doing that because if you use the left to right number, it would be a 4-methylpentane. But as you can probably see, if you use the gold numbers, it's kind of hard to see. My pen kind of crapped out there. That methyl group is off the second carbon. So see, scientists could call this 4-methylpentane or 2-methylpentane. And in organic chemistry, it's always about smallest number, longest chain. So 2 is better than 4 because 2 is smaller, 2-methylpentane. Anyway, this is the kind of process you want to do in this problem. And you can probably see that you could move the methyl group over 1 carbon to the 3rd position. That would be a 3-methylpentane. If you move the methyl group to the 4th carbon, it would feel like it's 4-methylpentane. But if you look at the green numbers on top, 4-methylpentane, like we talked about, is also known as 2-methylpentane. So that would actually be the same compound as I've drawn right there. Anyway, there's also 2 dimethylbutane isomers of this. So if you draw them all out, here they are. I've kind of covered up there the N-hexane, but hopefully you can see that this is just 6 carbon atoms in a row. It's just 6 carbons in a row. That would be N-hexane. And right below it here is 2-methylpentane. And again, notice you need to count both left to right and right to left. Right to left makes this 2-methylpentane. If you put down 4-methylpentane, at least the scientists could figure out what it is. But it's kind of like saying, I ain't knowing what's going on. You kind of sound like a hick. You have to use smallest numbers if you want to be a cool scientist, all right? So 2-methylpentane. Below that is 3-methylpentane. 4-methylpentane we saw was the same as 2-methylpentane. You might think that there's a 5-methylpentane, but 5-methylpentane, if you count the longest carbons, 5-methylpentane actually becomes a 6-carbon chain. Sometimes the carbons will roll around on you, and that's okay. So, quote-unquote, 5-methylpentane is just N-hexane again. Finally, there in the lower left, you have 2,2-dimethylbutane. So again, if you count right to left, you get 1, 2, 3, 4, and notice how each methyl group gets its own number. That's because on the next example, you can see where, regardless of which way you count, you have methyl groups off the 2nd and the 3rd carbons. So that would be 2, 3-dimethylbutane. So these are the 5 isomers. There's lots of other things you can draw, but I will guarantee that the other ones you draw are going to be one of these 5. You have to reconfigure it a little bit. But anyway, all of these problems with isomers, remember, it's all about carbon getting 4 bonds. And then once you get these structures, look for longest chain and smallest numbers, and you'll be good to go. So here's a compound listed on the right, and it says give the systematic name for an alkane shown on the right. Well, man, most important, longest chain and smallest number, okay? So one thing, for example, for the longest chain, you could try doing, in America, with the English language, we're so used to reading left to right. So maybe you think that this underlined part right here would be the longest chain. And if you count with the carbon on the left, that would be 1, 2, has that CH2, CH3 thing, 3, 4, 5 has a CH3 above 6. So that would be a hexane. All right, that would be the quote-unquote longest chain. We have a methyl group on the top and an ethyl group at the bottom. And ethyl comes before methyl. So this would be a 2-ethyl-5-methyl hexane. Usually the ethyl group then, if there's a choice, would get the smaller number, not the methyl. And that would be one possible name here. However, sometimes the drawings will lie to us, like they won't exactly show you how the molecule will be in the longest chain form. So as an example of that, let's try an alternative numbering system. And if we get more than 6 carbons in our chain, we've done something right. And in this alternative system, I want to start at the methyl of this ethyl group instead. That's going to be number 1. And then 2, 3, 4, 5, 6, 7. Oh my gosh. So, big surprise. All right, I'm the teacher. Of course, I know these things, right? All right, Prof. back on. Anyway, you get a longer chain of carbon atoms when you include at least the ethyl group. Now, I circled the upper methyl group. You could have also circled this right-hand methyl group and you'd get the same answer, okay? But the important thing here, you want to look for the longest chain. So while the other compound was an ethyl-methyl hexane, this compound circled with 7 carbons is going to be a heptane. Heptane is a 7-carbon system. We have 2 methyl groups that aren't part of the longest chain. One of them's right there in blue, and the other one is right there in blue, so the left and the right-hand side. So this is where you want to look for the smallest numbers possible. So if you start down here at ethyl again, it would be 1, 2, 3, so that methyl group would be a 3, 4, 5, 6, 7. So, 7 would be up there actually, my apologies. So the methyl groups, in the way I've numbered it right now, they would be off the 3rd carbon and the 6th carbon. So you would think at first, you might call this 3, 6 dimethyl heptane, all right, where the 3 and the 6 show you the positions of the methyl groups. But don't be done quite yet, because like I said, I really recommend that you count in both directions. So for this problem then, I'm going to start in the upper CH3. So instead of being number 7, this would be number 1. And this carbon would be 2. And look, there's a methyl group right there we're going to call it. 3, 4 is the same. 5, this methyl group is going to be a 5, 6, 7. And lo and behold, if you count up those numbers, then the dimethyls are not at 3, 6, they're at 2, 5. So remember, longest chain, smallest numbers, 2, 5 dimethyl heptane would be better than 3, 6 dimethyl heptane. So this is what you kind of have to do, especially when you're learning on how to name things. You've got to go through and find the longest chain, all right? So in this drawing here in the lower right, you can see I've highlighted the heptane part. It's not a hexane. And the methyl groups and stuff, you might at first think they're 3, 6 dimethyl, but really it's 2, 5 dimethyl heptane. Try counting in both directions. The smallest number is key. Oh boy. This is why a lot of times people go into organic chemistry and they kind of get snowed over, because this is very unusual stuff compared to the things we've looked at so far. But going through these examples now, you're going to be really strong and ready if you do go into organic chemistry. In this question, if you look at it carefully, we're going to look at alkenes, E-N-E, and alkenes have a double bond in them. So alkanes are all sp3, tetrahedral, stuff like that, but alkenes will have a double bond, so they're a little bit different. And what I'd like you to do in this problem is draw and name the 5 alkenes with the formula C7H14, and I want them all to have straight chains. Now a straight chain just literally means that it's going to be 1, 2, 3, 4, 5, 6, 7 carbons in a row. 7 carbons in a row is a straight chain, a lot of times in organic chemistry. And then somewhere in that 7 carbon chain, you're going to have a double bond. So you wouldn't, for example, have like a carbon coming off here. No. They're all going to be in a straight chain together like that. So you can imagine you could have a double bond between the first 2 carbons, or you could say have a double bond between the second carbons. Because they are straight chains, you have 7 carbons in a row. So for example, let's put the double bond back there between the first and the second carbons. Now remember, carbon can only handle 4 bonds. That's the maximum number. So in this case then, there would be 2 hydrogens off that carbon, because then that carbon has 1, 2 bonds to hydrogen and 1, 2 bonds to carbon. That's its 4 bonds. Now the other carbon with a double bond has 3 bonds to carbon. It has a double bond to the carbon on the left and a single bond to the carbon on the right. So there would only be 1 hydrogen off that one. But the other ones would all have 2, except for the last one, which would have 3, stuff like that. So when you're naming these, it's an alkene with 7 carbons. 7 is hept. So this would be a heptene. And you need to tell, as we'll see, where the double bond starts. This compound would be 1 heptene. And the newer system, which is you're welcome to use, you could also call this hept 1 ene. Again, the 1 just says where the double bond starts. So 1 heptene or hept 1 ene would be fantastic. So as you go through these then and figure out what they are, there's going to be 5 of them, and we'll talk about them here. So first of all, right here, the first one is 1 heptene. All right, no problem. But if you look here, there are 2 heptenes and 2 3 heptenes. And at first you're like, what the heck? Well, a double bond does not rotate in solution. It stays very rigid. It takes a lot of energy to break that double bond and make it a single bond. So notice the orientations of the hydrogens. On the left-hand side, the hydrogens are on opposite carbons, but they're the same side. And the one on the right there has hydrogens that are on opposite carbons and opposite sides. So these are called cis and trans isomers, and it's very difficult to convert a cis into a trans or a trans into a cis. It's more than would happen normally. So that's why this becomes important when it comes to these crazy double bonds. You can have cis and trans. Now notice that the first one, and the one I drew in green, does not have cis and trans. That has 1, 2, 3 hydrogens around it. If you have 3 hydrogens, you can't have cis and trans. You can only have cis and trans if there are 2 pieces that are the same. So in the 2 heptenes there, you have 2 hydrogens. Those are the same, all right? So they can have cis and trans on them, but you can't have it on the first one. Likewise, if you move the double bond over to where it begins on the 3rd carbon, then you can have cis and trans 3 heptene or trans hept 3 ene, stuff like that is fine. So no problem. Now it might be tempting to say, hey, why not have a 4 heptene? So 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, this would be the 4th one. Let's put a double bond right there. So if you have a double bond, this looks like it could be a 4 heptene. But if you remember, you need to kind of figure out smallest numbers. So left to right, it would be 1, 2, 3, 4 heptene, absolutely. But if you count right to left, it's 1, 2, 3 is where the double bond starts. So quote unquote 4 heptene is really 3 heptene. It's the smallest number, and you need to rotate these in your mind back and forth. So 4 heptene quote unquote is really 3 heptene, and likewise a 5 heptene quote unquote would be like a 2 heptene, stuff like that. So it's very important to rotate these in your mind and see what's happening. So double bonds, ene ending, and double bonds can have cis cis and trans isomers with them. They'll only have cis and trans if two of the pieces around the double bond are the same. They have to be on opposite carbons, and you can have them same side, which is cis, or opposite side, which is trans. Crazy stuff, but nothing you can't do. In this question, you need to draw some structural formulas for these compounds. And what I kind of want you to do here is focus on what kind of compounds they are. So on 9A, notice that there's an OL ending. And OLs mean alcohols. Alcohols are carbon compounds with an OH on them. And the 1-ol and the 2-ol, the 1 and the 2 tell you where the OH is going to be. So butane would be 4 carbons in a row. Butane 1-ol would have an alcohol off the first carbon, and butane 2-ol would have an alcohol off the second carbon. So when you draw them out, here's the 4 carbons. 1, 2, 3, 4. 1, 2, 3, 4. And you can see that that alcohol group, that's the OL, it's off the first carbon and the first structure, and the OH, which is right there, is off the second carbon and the second structure. That's why there's butane 1-ol and butane 2-ol. Now the next one, if you break this name down, it's an ethane. Ethane is a 2-carbon alkane, so it would be like CH3CH3. However, there's a dibromo on there. Di means 2, bromo means bromine, and you can see that they both have number 1 by them. So what that means is of the 2-carbon system, both of the bromines are going to be off the first carbon. So 1,1-dibromoethane will look like this. So again, ethane would have 2 carbons. 1,1-dibromo means 2 bromines, and they're both off the first carbon. Oh boy, you could have a 1,2-dibromoethane. You'd have one of the bromines off the second carbon, but as you can see in the structure, both the bromines are off the same carbon. That's why it's 1,1-dibromoethane. Now on C, we've got another alcohol. It's off the second carbon, and you can see there's a bute. So butane, butyl, is a 4-carbon system. So on our 4-carbon system, the alcohol is going to be off the second of the 4 carbons. And on the third ones right there, you have dimethyl. So a methyl group is CH3. You have not 1 but 2 methyl groups, and they're both off the third carbon. So I would start by drawing 4 carbons in a row. I would have an OH off the second carbon, and off the third carbon, I would have not 1 but 2 methyl groups. So if you do that, here's the structure: 3,3-dimethyl butane 2-ol. Oh boy. So again, here's 1, 2, 3, and the fourth one is a CH3. You can see how the second one right there has the OH off of it, and the third one has a methyl group, both quote-unquote above and below. They're both off the third carbon. Good to go. D has a YNE ending. YNE is an alkyne, a triple bond. So if it was just 1 butine, you would have butyl, which is a 4-carbon system like butane. The triple bond would be between the first and the second carbons. Triple bonds, the number says where the triple bond starts. And then the third carbon, you can see, has a methyl group off of it. So start by drawing 4 carbons, the bute. YNE means a triple bond between the first and second carbons, and then the third carbon will have a methyl group off of it. So there's the structure for 3-methyl-1-butine. So you can see it's 1, 2, 3, 4 carbons for the bute, and then the triple bond starts at the first carbon, and the third carbon has this methyl group off it as well. The next one, cycloheptane. Hept is 7. Cyclo means they're all going to be like in a ring. So you would have 7 carbons kind of in a ring system. It's kind of weird to draw a 7-carbon system, but you can totally do it. They would all be just sp3, which means 4 bonds total, all single bonds, so a lot of hydrogens. There's the structure for cycloheptane. So you can see there's 1, 2, 3, 4, 5, 6, 7 carbons in a chain, like kind of a circle, all right? And each carbon has 2 hydrogens off of it because carbon has to have 4 bonds total. Cycloheptane. The next one, diethyl ether. Ethers are oxygens that are between carbon atoms. So ethyl is CH3CH2. Di means 2 of them. So you're going to have a CH3CH2, then you're going to have the oxygen, and after that you're going to have the other ethyl, the other CH2CH3. So diethyl ether structure looks like that. Ethyl groups on both sides. Now the newer, fancier name for this compound is ethoxyethane. You take arguably the smaller alkyl group, call it an oxy, and the longer alkyl group is an alkane. We'll see this a little bit here in the next one. But diethyl ether is almost always called diethyl ether. It's a very common name for that structure. Now on G, you have an oxy. So that means you also have an ether. You have a 2-methyl. So you have a methyl methoxy. You have a methyl group connected to the oxygen. That's what methoxy means. And propane would be 3 carbons in a row. Off the second of those 3 carbons is where the methoxy group goes. So on G, here's the 3-carbon system. 1, 2, 3. 2-methoxy. CH3O is the methoxy group. It's off the second carbon of the 3-carbon propane. 2-methoxy propane. That's the newer way of calling ethers, by the way, and probably it's better. The next one is an oic acid. That's a carboxylic acid. Carboxylic acids are C double bond O with an OH next to them. And you can see there's hex. Hex is the prefix for 6. So I would start off by having 6 carbons in a row. And at the end carbon, I would have the double bond OH, and that would be carbon number 1. And next to it, on the second carbon, you would put a methyl group. So here's 2-methyl hexanoic acid. You've got 1, 2, 3, 4, 5, 6 carbons. 1 is always the carboxylic acid, and 2-methyl means you have a methyl group off the second carbon. 2-methyl hexanoic acid. Acetic acid is a really common carboxylic acid. Acetic acid is also known as ethanoic acid. Ethanoic acid is just CH3COOH. You can see again it's a carboxylic acid. Acetic acid is the active ingredient in vinegar. So if you put vinegar on a salad or something like that, you are using acetic acid. Kind of cool. Trimethylamine is a nitrogen-containing species. Nitrogen can have up to 3 bonds, and it usually has a lone pair. Each of those bonds has a methyl group on it. That's what the trimethyl part means. So trimethylamine would be a nitrogen. Nitrogen has a lone pair. There's a methyl group off each one of them like that. Trimethylamine. The last one there is ethyl methylamine. Notice they're alphabetical, which is what you want to do. Ethyl is CH3CH2. Methyl groups is CH3. But we talked about how trimethylamine, nitrogen can handle up to 3 alkyl groups around it. But there's only 2 alkyl groups listed here. That means the other position is just going to be a hydrogen atom. So ethyl methylamine has a methyl group, CH3, which is that group on the right. It has an ethyl group, which is CH3CH2, and then the last position is just a hydrogen. These are some of the organic compounds that you'll see if you take the class. It's all stuff you can do. Just kind of break the names down. And again, look for the number of carbons. Always start with that and then go out from there. Here are some structures, and I'd like you to figure out the names of these compounds. So this first one right here, carbon with a double bond O, is called a carbonyl, and the carbonyl is between 2 alkyl groups. A carbonyl between 2 alkyl groups is called a ketone. And if you have a ketone with 3 carbons, that would be propane if it was an alkane. But this compound is a ketone. This would be propanone. However, nobody calls it propanone except for weird chemists, basically. The far more common name for propanone is acetone. You can buy acetone at Fred Meyer's and places like that. Propanone is the formal name and acetone is the common name, and it's a ketone, an example of a ketone. Now the next one has a carbonyl as well, the C double bond O, but notice that it's next to a hydrogen. And believe it or not, that's enough to make this a whole different kind of compound. It's called an aldehyde. And for reasons which we don't have time to go into in Chemistry 223, that hydrogen next to it gives it a whole different reactivity. So to name this, count up all the carbons, 1, 2, 3, 4. 4 carbons would be butane if it was a straight chain alkane. But because this is an aldehyde, butane becomes butanal. Butanal is an aldehyde. Notice the Al. The Al will tell you it's an aldehyde. You don't need a number for this because the aldehyde is always on the end next to a hydrogen, so you don't have to worry about that. The next one has another carbonyl. The carbonyl is between a carbon methyl group on the left and a propyl group essentially on the right. So this is another example of a ketone. But the different part here, though, is that the carbonyl could be on the second carbon, which is what we have here, but in theory you could have a carbonyl on the middle carbon, the third carbon. So if there's a choice where the carbonyl goes, you do need a number. So because there are 5 carbons and this is a ketone, this would be a pentanone. Pentane would be the name of the alkane. We'll add ONE to it because it's a ketone. And because there's a choice where the carbonyl goes, we're going to call this 2-pentanone, because you could definitely have a 3-pentanone if you move the carbonyl over. D has a benzene ring, and the benzene ring, benzene, will be the base of this. And next to it you have a chloro Cl and a nitro NO2 group. So we're going to call this a chloro-nitro-benzene, but you could have the chloros and nitros at different positions, so we need some kind of numbering system. I would recommend using smallest numbers possible, 1, 2, 3, etc. I would call this 1-chloro-2-nitrobenzene. However, sometimes you will see what's called ortho, meta, and para nomenclature. Ortho is a 1-2 nomenclature. So if you see orthochloronitrobenzene, same thing. So 1-chloro-2-nitrobenzene is the same as orthochloronitrobenzene. Either one is fine. The next one has 2 nitro groups on benzene, so it's a dinitrobenzene. You could call this 1,4 dinitrobenzene. You could also call this para dinitrobenzene, and either way is fine. So ortho is 1,2, para is 1,4, meta, which is not as common, is 1,3. These are all examples of aromatic compounds, which has an extra set of stability. The next one has a chloro and an ethyl group. So again, chloro comes before ethyl. Now notice that this one is written on its side, and it might be tempting to think that high noon would be 1, chloro would be 2, ethyl would be 3, etc., etc. But you can rotate these crazy organic molecules any way you want. So chloro is actually number 1, and ethyl would be number 2. This would be 1-chloro-2-ethyl-benzene or ortho-chloro-ethyl-benzene. Either way is fantastic. G is an example of an alcohol. You have 1, 2, 3, 4, 5 carbons in there. I would have called this compound a 2-pentanol because the OH is off the second of 5 carbons. Pent is 5-pentanol, but you could also call this pentan-2-ol. Either way is fantastic. I only listed the old school method there, which is fantastic. 2-pentanol is a great name for this compound. But again, if you called this pentan-2-ol, that would be fine too. The next one is an aldehyde. It has a carbonyl, C double bond O, next to a hydrogen, so that means it's an aldehyde. And the longest chain of carbon atoms, which you need to name this, it would be 3. either 3 the way I circled it, or you can include the lower CH3 and not include the CH3 on the left. Either way is fine. Either way, there's a methyl group that's not part of that 3-carbon chain. So if it was just a normal 3-carbon chain with an aldehyde, it would be propanal, but there's a methyl group right there. We need to make sure that everybody knows that methyl group is there. So 2-methyl propanal would be the name. It's an aldehyde. And then finally, the last one there, it's a carboxylic acid. It has C double bond OOH, which is carboxylic acid. We have 1, 2, 3, 4 carbons. 4 carbons as a carboxylic acid would be butanoic acid. So we would call this compound butanoic acid. Now, if you cheated and looked up what the structure is on Google, you'll probably get butyric acid. That's the common name for this acid. But again, I want you to know the formal names more than the common names, at least on these kind anyway. So try to use butanoic acid, at least for now. And after a while, when you get good, you can call it butyric acid, and I'm totally happy with it. This last one, I'd like you to give the official organic chemistry name for these compounds. And these are all common names, and some of these we've probably looked at already, but if you haven't seen them, I just want you to know what they are. So acetone, we saw earlier, is an example of a ketone with 3 carbon atoms. This would be propanone. So the more formal name here for acetone is propanone. Just realize that they are one and the same thing. Toluene is an example of a benzene compound that's very common. If you put a methyl group on benzene, that's what toluene is. So toluene's official name would be methylbenzene. It's a C6H6 where one of the hydrogens was pulled off and a CH3 was placed in its stead. Toluene is pretty common. You'll find it at local stores and stuff like that. Acetylene is what people use when they weld. Acetylene has a lot of energy, so you need something that's going to have a lot of stored energy, which is great if you have a triple bond. So acetylene is a 2-carbon alkyne. It's formally known as ethyne. So acetylene is again the common name, and ethyne is the more official IUPAC organic chemistry name. Same thing. Formaldehyde, which is used in funeral services, is a type of an aldehyde with only 1 carbon. So formaldehyde with 1 carbon, an aldehyde with 1 carbon, would be C double bond O with an H on both sides. Methanal would be its formal name, but again, almost everybody calls it formaldehyde, so no big deal. Acetaldehyde is something you might hear about a lot more in organic chemistry. We haven't talked about it here very much, but acetaldehyde is essentially just an ethyl group, CH3CH2, where you have an aldehyde off one of the carbons. So ethanal would be the formal name of acetaldehyde. You'll learn about this more in organic chemistry. I'm just kind of giving you ready for what you might see in the future. Finally, ethylene, which helps keeps our bananas stable until they get up here from Central America and places like that. Ethylene is a 2-carbon system. It would be ethene. It has a double bond. So ethene and ethylene, same compound, different names. Obviously, more people call it ethylene than ethene, but now you know the difference. Okay, so that's it for problem set number 6. I appreciate you being here, and I hope this has been useful. There are study guides and concept guides for both Chapter 19 and Chapter 21, and I encourage you to check them out. There's also the online chapter guide you can check out for more information and ways to study this material. The organic chemistry guide, I think, will be helpful, so there's lots of ways to assist you with learning this material. And again, don't feel like you have to be an expert in any of this. Just kind of have a general understanding of how this all works out. Okay, thank you for spending your time with me on this problem set and all the other previous problem sets. I really do appreciate it. Good luck with your studying. Have a wonderful day.